Welcome to ICANX Talks, Connecting the World and the Universe. I am your host, Professor Martin Thuo, coming to you from the Eastern United States from North Carolina State University. This month, we are exploring this subject of soft matter. We have had Professor Neshev, Professor Wheeler, Professor Chen, and today we are very privileged to have Professor Pei from UCLA. In today's panel, I'll be assisted by Professor Zeng, Professor Gifney, Dr. Andrew Martin, and Dr. Daniel Siller. Our speaker today, Professor Pei, is very well established. He's a professor in the Department of Material Science and Engineering with affiliation in mechanical engineering at the University of California, Los Angeles, UCLA. He specializes in functional polymers and nanocomposites and is very, very well published with over 220 papers. He has over 45 granted patents and many more pending. And it's a witness to his creativity and the creativity of his team. He directed UCLA Soft Materials Research Laboratory, which is interested in studying artificial muscles, flexible electronic materials, plastic scintillation, electrochromic cooling devices, among many other things. He obtains his bachelor's degree from Nanjing University and his PhD from the Institute of Chemistry, Chinese Academy of Sciences. He was a postdoctoral fellow in Linköping University, Sweden, and worked at Unix Corporation, which is now DuPont Displays, and SRI International. He has been a full professor at UCLA since 2004. He's a fellow of SPAE. He's affiliated with ACS and MRS and serves on several editorial boards of several journals, including Advanced Electronic Materials and Scientific Reports. And his resume is pretty extensive, so I am not the speaker, so I'm going to hand over to Professor Pei so he can share with us his amazing work. Professor Pei, welcome.
Let me share my screen first. All right, do you see my screen?
Yep, we're good.
All right. Well, thank you, Professor Matthew, for the generous introduction. And hello, everyone. And I'm Qibing Pei from the Soft Materials Research Lab at University of California, Los Angeles. It gives me great pleasure to introduce this research and our thoughts about functional dielectric polymers and electromechanically active devices. So I start with that a lot of these materials and are used in the form, as you see here, a thin film of this functional material and a pair of compliant soft conductive material. So many of these share sort of the same requirement of utilizing a dielectric material. So in our case, we mainly use a dielectric polymers, a semiconductor material, and a conductor. So since that our goal is to have soft devices eventually, so all of these materials need to be intrinsically flexible and ideally stretchable so that the whole device is stretchable. So today I would like to share with you mainly focusing on dielectric polymers. So these are the three main categories of dielectric polymers we touch on. One is dielectric elastomers that generate larger actuation strain with the molecular artificial muscle, so mainly for to reproduce the function, the motor function of muscles. The second one is bistable dielectric elastomers. So the application we are looking at is mainly for tactile devices. And the third one is electrichloric polymers. So this polymers have a large entropy change during voltage on and off. So we are looking at utilizing this category of polymers for solid state cooling. All right, so dielectric elastomers. So basically, it's a thin rubbery film sandwiched with compliant electrodes. So when you apply a voltage, I mean, most of the time we apply quite high voltage across this polymer film. So this is like a variable capacitor because the electrode and the polymers are all compliant and deformable. So the voltage applied, so you try to flow current through this polymer film, but the polymer is not conductive. So charges are accumulated on the electrodes. So the same charges on the electrode would repel each other, while the opposite charges would attract each other across the film. So since the film is soft, the film will be squeezed in thickness, and rubbery polymers, their volume does not change. So when they reduce in thickness, their area will expand. So the image to the right here shows, let me turn on my, see, oh, excuse me. Let me see if I can turn on the laser pointer here, never mind. So the image to the right here shows a dielectric elastomer polymer. And in this case here, this dielectric elastomer is a commercial adhesive film, the VHB acrylic, manufactured by 3M as a general industrial adhesive film. So you could also use another important type of dielectric elastomer, the silicones, which you can buy the resins and dissolve in the solvent and cast films on it. So the VHB film here is pre-stretched biaxially by 300% or 400%. And the dark material is coated. This polymer film is transparent. Okay? So the dark color you see there is carbon grease applied on the surface as the compliant electrode. So when you apply a voltage on, you will see that the film gets squeezed, its area expands. So when the voltage is removed, the film contracts. So voltage on, off, so you see the film repeatedly expand and contract. So the physics behind this dielectric elastomer is quite simple in a way. You know, this the electrostatic pressure or the Maxwell pressure is proportional to the dielectric constant of the dielectric elastomer and the square of the electrical field applied across the polymer film. So typically, the polymer films we use, the thickness-wise, is around 30 to 40 microns, and the high field, the true field applied to the film is on the order of 100 to 400 volts per micron. So we're talking about applying a voltage here that's on the order of a few kilovolts. So this is a high voltage applied to this variable capacitor. Okay, so with the electrostatic pressure here at the applied true field of 100 volts per micron, that pressure is on the order of about 1 megapascal. Okay, that's a very high pressure. So the human muscle, we can generate a pressure usually less than 100 kilopascal. So this the pressure, the Maxwell pressure here, we're talking about something that's 10 times higher than natural muscle. The strain in the film, if the modulus of the polymer is Y here, and then the stress or the strain, the thickness is shown as this equation here, SZ, and the area expansion corresponding to the thickness reduction is shown also in this equation. So in the video here, we see the area expansion of about 100%. So that's we in the field we often the number we quote because that's the area expansion is relatively easy to measure. Yeah. So the dielectric elastomer. So one of the major benefits is that the responding is fast. So when you apply the voltage on expand, remove the voltage, shrink back immediately. But in reality, that the response speed of your actual actuator or devices will depend on a number of different factors. So the first come to mind is the viscoelasticity, and most of the time, if your actuator, the dielectric elastomer actuator, shows a limited response speed, it's probably the polymer is viscoelastic. Okay, so, but I mean, from the final device point of view, it's not just the material issue. It could also be the mechanics or the circuit issues, because with a soft actuator or a soft motor, so the mechanical inertia can come into play when it carries a high load. And if your electrical resistance is not low enough, you may also have the RC constant come into play. Okay, like this one shown here, that if the electrical resistance, say 1 mega ohm, and the capacitance is 10 nanofarad, and then you will see the time constant of 0.01 second. So meaning that your circuit can only drive this device at 100 hertz. But most of the time, we can relatively easily make the electrical resistance less than 1 mega ohm. So the RC constant is I mean, but most of the time for actuator application is not an issue. But if you are designing a generator based on these kind of materials, it could become an issue. So again, that so the first limiting factor for response speed is the viscoelastic behavior of the material. So in this video, we just saw here that the response speed is it looks. Let me play it again. So kind of on and off relatively slowly. And this is a VHB film. Okay, so once you plasticize this VHB, so in a way spray a plasticizer like a DOP, dioctyl into this polymer to reduce the viscoelasticity, you will see that its response speed can be significantly increased. Let me play this video here. So the actuation here starts at 1 hertz, the same peak voltage, and the frequency is ramped up to 5, 10, 20, 50, and 100 hertz. So when in dielectric elastomer film at about 100% area expansion here, and the power density at 100 hertz is extremely high, okay? So that shows that when the viscoelasticity is removed, and you will see that the dielectric elastomer can respond at a high actuation strength at a high frequency. All right, so these are soft rubbery films. So to deliver high force output or power output, so we have to stack this polymer together. There are many efforts out there to stack dielectric elastomers, thick stacks to generate a high thickness stroke and high force output. So one of the approaches we took was to make this kind of we call spring rolls. So you first stack 2 dielectric elastomer films with carbon-based electrode, and then you wrap this 2-layer stack around a central spring. Okay, so when all is done, these VHB films are under high pre-stretching conditions. So the finished spring roll, as the image to the right showing there, so you can easily make a sort of a centimeter size actuator in a laboratory scale. And this video here just shows that this spring roll lift a 1 kilogram mass. Okay, so use this kind of linear actuator with when you apply voltage extending length, and we can sort of design a simple robot. As this one shown here, it has 6 legs. If you look closer, you will see that the 6 legs are tilted at different angles. So I mean, the one to the front or to the left here is to lift the height. The one to the right is at the larger tilting angle. So this is to push against the ground. Okay, so and the 6 legs are actuated in 2 tripod modes. And this is when the robot is supported, and here you will see that it can move. And if you ramp up the frequency at the same maximum voltage, and so it will move faster. Yeah. So that's one linear actuator. And to make it more functional, and what we can do here is that while we wrap the films, the electrodes are already patterned into as shown here, so that when the films are wrapped around the spring, the electrodes align on 4 different circumferential spans on the spring. Okay, so we can activate the different spans to cause it to bend to different directions. Like this image shown here. So this the 4 different spans are connected, and now we activate the different spans to cause it to bend. Okay, so obviously that you can ramp up the frequency. And use this kind of 3-dimensional spring rule. Call it 3-dimensional because it can be made to bend, and also when multiple spans are activated, the spring will extend in length. So you can truly have a 3-dimensional deformation from this spring rule. And this image just popped up here is a simple robot that has 6 of these 3D spring rules. They are also activated in 2 tripods. Okay, and you will see here that the robot can move. Yeah. So with this kind of direct actuator used as the legs, robot design becomes much simpler. All right, so the high performance from those dielectric elastomers, VHBs or silicones, are generally obtained from highly prestretched films. So the image to the right, upper right, showing that the VHB, when it's biaxially prestretched, so you will see the expansion in 2D. Okay, so in the flat film, the area expands circular to larger circular areas. And the lower left shows a film that was uniaxially pre-stretched in the horizontal direction. So when you apply the voltage, the actuation is shown here mainly in the vertical direction. So why pre-stretching makes such a big difference, in a way, significantly improves the actuation performance. So from a experimentalist viewpoint, so I plotted the chart here. The red curve shows the typical stress strain behavior of a dielectric elastomer. So what you see here is there is a large stress strain plateau. Okay, so and when a constant voltage applied, so the voltage causes the film to deform. And as you increase the voltage, the strain from the maximum stress increases. But that there is an issue here is that you see the equation showing that the maximum stress is proportional to the square of the typical thickness. So which means that as at a constant voltage, when that voltage causes the film to expand, as the film expands, the thickness reduce, the field increase. Okay, so we have a positive feedback loop here that at the same voltage, the film becomes thinner by the same voltage because the field increases. So eventually, this positive feedback loop will cause the dielectric elastomer to a high strain, crossing the dielectric field strength of the polymer. So there will be a dielectric breakdown. Okay, so the stable actuation you can get from this film is limited because of this electromechanical instability. Okay, what the pre-strain does here is that it narrows the plateau of the stress strain behavior so that when the true field rise to a certain level, it will see a rapid rising of the stress or the stiffening effect of the dielectric elastomer. So you cannot expand it infinitely. So we can achieve a much larger stable actuation strain from this pre-stretched film. So Professor Xuanhe Zhao and Zigang Shuo introduced this beautiful theory to explain the electromechanical instability. And so basically that dielectric elastomer, they categorize this dielectric elastomer into three different kinds. Type 1 is a stiff one. And in this chart here, the red curve is the breakdown field as a function of the stretch ratio. Okay, so assuming the breakdown field is a constant, so then the breakdown voltage varies with the stretch ratio. So with a stiff material or the type 1, the maximum strain you get is relatively small. Okay, so if the rubbery polymer is soft and the strain or stretch ratio lambda here increases with the voltage applied, but when the voltage reaches a certain level, you will see a equivalent stretch ratio point, or that's a slap through. So which means that the maximum stable strain you can obtain from this kind of type 2 soft dielectric elastomer is only lambda equals to 1.26. So the pre-stretched film shows a different stress strain behavior. It allows you to drive the film to a much larger strain at the lambda limit here. Okay, so this is how the pre-stretching works for the dielectric elastomers to boost the maximum actuation strain and the stress. Yeah. So pre-stretching works beautifully, but it's practically problematic because highly pre-stretched elastomer film will fatigue over time. So they generally have limited shelf lifetime. So one way to overcome this issue, so we introduce here is making an interpenetrating polymer network dielectric elastomer, or the IPN DE. So the way to prepare this film is starting with the VHB film, pre-stretch it biaxially by 400% or as much as you can pre-stretch the film. Then you spray a acrylic difunctional acrylates, like or trifunctional, like the one shown here, TMP, TMA here. So this compound will diffuse into the polymer, and then it get UV cured, and then you relax the film. The film will not relax onto the original shape because of the additive forms its own network to support the network structure. So in the finished freestanding film, you have the original VHB network in tension, while the additive network in compression. So this kind of IPN film, I see here that the stress strain behavior, the right chart shows the stress strain behavior, where the stress strain plateau is narrowed so that above stretch ratio of 2, you see rapid rise of the stress. Okay, so, and because it's a freestanding film, when you actuate it, you see here, in this video showing here that the film, because the surrounding area is not stretched, so the film just shows buckling. Okay, so to be able to measure the area expansion of this IPN film, we have to put it on the diaphragm. So this image to the left shows the film on the diaphragm. There's a diaphragm chamber behind the film, and when you actuate it, okay, so the air pressure inside the film will keep the film expanded. Okay, so what you see here is an area expansion of over 200%. Okay, so the maximum true field is 420 volts per micron. So that represents a Maxwell stress on the order of several megapascal. So the IPM film also works well, and there's another way to do it. Okay, so to eliminate the stretching operation during the fabrication of the IPM film. So we borrowed this concept introduced by James Mark many years ago, and basically for elastomer with a single network length. Okay, so and the typical issue, if the segment between the cross-link point, if the segment length is long, it's soft, or if it's short, it's stiff. So you do not readily achieve a stress strain behavior that has low modulus, but a rapidly rising modulus at a modest stretch ratio, say 100% or 200% strength. But if you introduce a second network into it, or in this kind of bimodal network structure, you have chain segments that are short and long. In this kind of bimodal system, you could modify the stress strain behavior to obtain the kind of relationship that we need for high strain actuation. So the materials we choose to design these is the one shown here. One is a long chain polyurethane diacrylate and a short chain diacrylate. So these two are mixed together and formulate into dielectric elastomers by modifying the ratio of the two different network formers. Okay, so and for example, in this chart here, the red curve shows when this the short chain compound is loading is 0%, and the loading increased to green is 2%, and blue is 5%. Okay, at 5% of the short chain network forming compound, so we have the stress strain behavior that's sort of narrowed to around a stretch ratio lambda 2. After that, the stress rises rapidly to counter against the EMI effect. The first formulations that we introduced recently, so we replaced both the long chain diacrylate and the short chain diacrylate you see here. So Erin in my group, she graduated already. So she formulated, she made hundreds of different formulations and settled down in this system where we have these two different diacrylates, and also we have a butyl acrylate added to modify the viscoelasticity of the system, and isobonyl acrylate to enhance the tear strength of the resulting elastomer, and a small amount of acrylic acid. So I will talk about the effect of adding the acrylic acid. So you see here in this chart to the left is the stress strain behavior of different PDA additives in the long chain network forming system. So the one that PDA 10%, okay, so the orange color shown here, that one shows the sort of the ideal stress strain behavior. And also shown here is the green curve. So that has a 2.2 parts, or roughly 2.2% of acrylic acid added. And it has similar stress strain behavior. And actuation wise, so the orange and the green curve here shows similarly high actuation strain. Okay, so at a nominal field of 120 volts per micron. So at this kind of strain, the true field is more than 300 volts per micron. So this kind of, so basically that this kind of polymer, in particular, this system, the green curve, okay, containing 2.5% acrylic acid, we call this as the PHDE, or processable high performance dielectric elastomers. I'll talk more about this. So this is the acrylic acid. So you will see in this chart here that without the acrylic acid added, it has a tan delta, the mechanical loss, or the visco elasticity measurement, about 0.22. So with 2.5 parts AA added, so the visco elasticity is reduced to only 0.1. And so this chart here is the PHDE that has the acrylic acid added. And you see the film. So again, it's the film is mounted on the diaphragm chamber. Here, the chamber is placed above this dielectric film. Yeah. And let me see if I can. Maybe I just play this video here. So in this video here, you see a PHDE film. Okay, not pre-stretched. And so with 4 sort of legs 3D printed. So when applied the voltage, the film expands, the overall mass of the system goes lower. And when you remove the voltage, as the film shrink back, so this small object, so students like to call this a small jumping robot, so it can jump to a certain height. And this PhD, so the nice part about PhD, not only because it has high actuation performance, and also because that it's from the precursor, and so the formulation is a bunch of compounds and liquid monomers mixed together. So from that liquid formulation, we can process it in different ways. Like this one showing here that. And this PhD precursor is coated on different substrate, cured. Then we can also spray coat carbon nanotube electrode and a binder, so that when the PhD films are stacked together, the binder sort of glue the PhD layers into, looks like multiple layers, look like a single sheet. So like the figure B shown here is a 10-layer PhD film stacked together. And we have 5 times 4 active areas in this 10-layer stack. And the lower right image is the SEM of the cross section, shows the nice interfaces. So basically in this 10-layer stack, the overall film behave like a single thicker PhD layer. Okay, so the actuation of this 10-layer stack is similar to a single layer PhD film, and in actuation strength, and also response speed. So the right chart shows here that the green bar is for the single layer, and the red bar is for the 10-layer stack. They show similar actuation strength up to about 20 hertz. And above that, like at 50 hertz, looks like the film stiffens quite significantly. So the strength measured is reduced to a much lower level. All right, so that's about PhD film, or the dielectric elastomer. So to fabricate a reliable, high-performing dielectric elastomer actuator or device, so the electrode is also an important aspect. So I mean, we typically use carbon grease or carbon nanotube. In this one here, I want to show that in this video here, and let me play this video here. So if you see closer, you will see a dielectric elastomer film, no coating on it. So actually, the electrode here is the salt water. Okay, so please, excuse me. Sorry about that. So the salt water here is the electrode. So and this film was actually to close to 100% in area expansion. And the lower images are from the work of Christoph Kaplinger, etc. at Harvard. And they showed that you can use a gel electrolyte, okay, as the electrode. And the gel electrolyte is transparent. So you can have a totally transparent dielectric elastomer actuator and a loudspeaker for this system. So the salt water, the gel electrolyte, both work well. But we have been trying, sort of a totally dry, compliant electrode material. So the carbon nanotube is the one that we have been exploring for a number of years now. And so carbon nanotube could be dispersed in the solvent and then you spray. And depending on the spray thickness, so you can have different sheet resistance. And so what this experiment shown here is that when the CNT layer is too thick, it's too stiff, it prevents the actuation strain. When it's too thin, okay, so and is the electrode cannot drive larger strain actuation. Basically, the carbon nanotube that will lose continuity at high strengths. So the sweet spot is around when the sheet resistance is around 100 kilo ohm per square. Like the left chart, the dark data points shown there. So at this kind of carbon nanotube coating thickness, so the actuation strength could well exceed 100% in area expansion. So another thing about the carbon nanotube here is that at 100 kilo ohm per square sheet resistance, this coating is extremely thin. So, and when it's very thin, when a dielectric shorting or dielectric breakdown happens, like this one showing here, and actually, so when you apply the voltage again to it, and there will be shorting. That shorting causes local heating. It will burn off carbon nanotube around the short. So after that, and the short is healed or fixed, and the actuation can resume. So this kind of self-healing behavior is useful if you care about the operational stability of or lifetime of the actuator. So shown here is if we use the carbon grease, and which is very convenient to use and very so consistently deliver high actuation strength. Okay, so with carbon grease electrode, and so when you operate to a certain number of cycles, you will see breakdown. Okay, so in a way, sort of a certain terminal failure of the actuator. With carbon nanotube electrode, it lasts longer, but there's a problem there because the carbon nanotube has sharp tips. Okay, those sharp tips in air can cause arcing of air around it. So what you see here is that the carbon SWNT electrode, and so over time the strain goes down. It does not sort of fail terminally suddenly, but the strain goes down because you have more and more CNT coating areas got sort of burnt off or healed. Okay, so eventually you lose the active electrode area. To solve that problem, so we tried dielectric oil, which worked fine, and we also used a water-based polyurethane. So it was spray coated over the carbon nanotube layer. So the WPU layer sort of shield the carbon nanotube tips from air to prevent the arcing of air around the carbon nanotubes. So the actuation stability is enhanced with this sort of a double layer carbon nanotube WPU electrode. All right, so and that's a dielectric elastomers. So it's the response is dynamic. Voltage on, expand, voltage off, it shrink. So we developed this bistable electroactive polymer or BSEP And this kind of polymer, we first introduced, so what the polymer we use is this terbutyl acrylate polymer. Okay, so after annealing, this polymer is semi-crystalline. So it's rubbery, semi-crystalline, and at room temperature, okay, so room temperature is below its glass transition temperature. So at room temperature, this is a stiff polymer. Okay, so you apply voltage, it will not actuate. But when you increase the temperature above its TG or 40 to 50 degrees Celsius, the film becomes rubbery. And now at the operation voltage, and the film will expand just like the dielectric elastomer. Okay, so if you maintain the voltage and let the film to cool down, it becomes stiff again. So now you remove the voltage, the film will not shrink back. Okay, to go back to the original shape, you just simply heat the film up without a voltage applied. So this kind of BSAP film offers this bistable deformation to different shapes through this combination of heating cooling cycle and the driving voltage. Okay, so later on so glass transition, the problem is that it has a quite wide range of glass transition temperature, which can cause some problems. So we introduced this kind of BSAP polymer where it has this monomer here, so stereoacrylate, which has 18 carbon straight chain to the acrylate. So in the network polymer, this 18 carbon chain crystallize at room temperature. So this polymer at the room temperature is a semi-crystalline stiff polymer because of the crystallization of the side chains. But when you raise the temperature above the melting point of the side chains, it becomes a soft rubbery polymer. Okay, so the operation mechanism is similar as the polyterbutyl um, uh, acrylate system, except that here the modulus change is via the phase changing of the side chains. And the chart here, to the left is different formulations or different concentrations of the stereoacrylate. The red curve is or the blue one. Let's look at the blue one here. It contains 60 weight% of stereoacrylate. So we see that around 40 degrees Celsius, the modulus varies by 3 orders of magnitude within a temperature range of 5 degrees C. So the right chart shows this polymer that it shows actually excellent shape memory behavior. So and it has excellent shape fixation rate and shape recovery rate. And with this PSAP polymer, so we should so at the rubbery state, okay, so the maximum strength we can produce from this polymer is about 60%. And the module to further increase the voltage, the stiffness of this polymer. So we made this composite. So where this used the bacterial cellulose nanofiber as a filler added into the B cell. Okay, so the BC nanofiber it swells in water. If you prepare a water swollen cake of this BC nanofiber. Okay, so you can have this cake, and then if you freeze dry it, you will have a BC aerogel. So you place that aerogel into this BSAP resin, the liquid formulation, and so this way that the monomers will diffuse into the aerogel. Okay, so then we compress it to remove the excess BSAP resin and cure it. So the resulting sheet. It's the BCEP composite. Okay, and it looks paper white. This composite, like the one you show to the lower right image shown there. And the storage modulus of this composite at room temperature is about 1 gigapascal, like a typical stiff plastic. And when it's exposed to moisture, the BC part softens. So the modulus drop by about 1 order of magnitude. When it's heated to above the transition temperature of the BCEP, it softens. Okay, so also by around 1 order of magnitude. If it's heated and water soaked, and both the BC network and the BCEP network softens. So the modulus of the composite drops to only like 10 to 40 kilopascal here. So the overall, the modulus variation here is 24,000 times. Okay, a very large modulus change from this system. And using the BCEP, so the main application we have been exploring is for Braille electronic readers. So there are different ways to make this kind of haptic display panels. A number of groups out there are studying this, including Herbert Shi in Switzerland and Federico Carpi in Italy. So, and here shows the approach we are taking. And we are here in this particular design here, we are actually not utilizing the high voltage actuation. We use the large variable stiffness of the BCEP film. And we have this carbon nanotube electrode patterned into a serpentine shape as the compliant dual heating electrode to administer the stiffness of the BCEP film. Okay, so the pressure into this chamber is supplied by a small pneumatic pump. Okay, so when the BCEP film is heated at the pressure applied, the film expand. It would push up a pin placed above it, and so this the lower right image or images shows Braille patterns displaying the UCLA in the haptic format. And this one shows this typical operation cycle of the BCEP of the BCEP panel. So starting from the lower left at the off state, so the film is flat. And then we turn on the heater to soften the film and then apply the pneumatic pressure on. So that causes this diaphragm dot to raise in height by 0.7 millimeters. And then the heater is turned off. And so the film stiffens. So with the pump pressure off, it maintains the shape. Okay, so and to recover to the original shape, we just turn the heater on again to soften the film. So the BCEP film actually have a number of other interesting outcomes. So one shown here is that this BCEP film is stiff. You know, you can handle it easily at room temperature. But when you place on skin, so this is a specific formula where the phase change in temperature have been reduced to around 28, 30 degrees Celsius. So when you place this film on the skin, the body temperature will soften it. And since the film is so soft at the body temperature, so it actually sticks to the skin. Okay, let me play this video to show here that this could be used as a reversible adhesive. So the film placed on the skin and the body temperature softens it. And at room temperature, it's semi-crystalline, so it's opaque. So when it softens, it's transparent, totally transparent. And this image here, this is Han Xiang in the video. And so he made this triboelectric based sensor on this BSEP film. And he have these 4 different sensors on 4 fingers. Use that to remotely control a drone. And another interesting, so I already mentioned that the polymer at the crystalline, semi-crystalline state is opaque. When it's heated, it's transparent. So we can use this actually coupled with a dual heating electrode to show this sort of smart window film. Okay, so we can reversibly control its opacity with dual heating. And so in new here and very recently also shown that we can by reformulate the B cells so that at room temperature, this film is clear. But when the temperature reaches 35 degrees Celsius, okay, so there is a phase separation occurring in the film such that it becomes opaque at the elevated temperature. So we have different designs of smaller window films based on the BSEP film. And the last polymer I want to introduce is the electrochloric polymers. So we were inspired by the works on relaxer ferroelectric materials, either the PZTs or the PVDF terpolymers. Okay, so these electrochloric materials have a large adiabatic temperature change up to 12 degrees Celsius. So basically that when you apply a field to this kind of material, as a dipole orient, its entropy reduced. So the material release a large amount of heat and the temperature goes higher. But when you remove the voltage, the dipoles relax, okay, the temperature goes down. So it generates reversible heating at the voltage on and cooling at the voltage off. So the relaxer ferroelectric polymer, like this PVDF, TRFE, CFE terpolymer, it has a very small hysteresis. Okay, so it's a relaxer ferroelectric. And here is a 2-layer stack of this terpolymer and 3 layers of carbon nanotube electrode. So let me play the video here. So when you apply the voltage on, the active area is heated because of the dipole orientation. Okay, so when the voltage is removed, it cools down. So you can using the voltage to reversibly control the temperature up and down. And to make it into a cooling device, we will need to transport the heat from the source to the sink. So the way we are doing that is coupled the electrichloric function with electrostatic actuation. So in this structure here, the electrichloric stack has the carbon nanotube electrode on the surfaces. Okay, so and then on the heat source and the sink, we have a conductor layer and a dielectric layer there. So when the conductor layer, a voltage is applied to the conductor layer on the heat sink and the carbon nanotube electrode on the polymer layer. So it will cause an electrostatic effect and move the film toward the heat sink. So if the voltage is applied between the heat source electrode and the CNT on the polymer layer, it will drive the film to the heat source. Okay, so let me play this video here. It's easier to see here. So this EC polymer stack is driven to the heat source and sink repeatedly. And so the electrostatic action here not only actually does the role of moving the polymer, which carries the heat between the source and the sink, It also that the electrostatic force here actually force the polymer film to contact tightening with the source or sink. Okay, so to improve the heat transport between the polymer and the substrate. So the lower right chart shows that the average heat flux at this same EC operation condition. Okay, so the black curve there. Okay, so as the electrostatic field is increased and the compression force between the polymer substrate is increased. Okay, so the heat flux is increased, from 0 volt field actuation to 60 volts per micron. So, and you see that the heat flux is increased by more than 3 times with the electrostatic force. And this electrostatic actuation does not add significantly any mass or volume to the device. So this allows us to demonstrate this pocket cooler where everything there, the majority of material there are polymers. Okay, so with PDMS and the PET and the stuff. And so with the voltage, so the EC voltage and the electrostatic action voltage synchronized, and we show that we can cool on one surface of this pocket cooler, and the heat is dissipated on the other surface. Okay, so and the fabrication process, most of this material here are fabricated through solution coating, and so we show in this one here that we can spray the terpolymer onto a fiber, and then overspray with a CNT layer to form this fiber cooler. Yeah. So while this the maximum adiabatic temperature change can reach 12 degrees Celsius, but that kind of operation condition is unstable. Okay, so for device fabrication, we have to lower the operating field to around 50 to 60 volts per micron. At this field, the temperature change achievable from the terpolymer is around 3 to 4 degrees C. That's not high enough for most cooling applications. So to increase the device temperature lift, so we introduced this cascade architecture. In this image shown here, we have 4 electrochloric polymer stacks cascaded into this. And the key element here, besides the EC polymer stack, is the thermal laminate sheet, which is when let's say the stack 1 and 2, or stack 2 and 3, in this one here, stack 2 and 3 here. So the heat is transferred between 3 and 2 through this thermal laminate. Let me play the video here to show. This is a single EC stack, okay? And here we have 2 EC stacks cascaded together. And here we have 4 EC stacks cascaded together. So what the cascading here plays is that from one EC stack, let's say the temperature change is delta T ECE. When you cascade this together, the overall device delta T is amplified. So in the simple, if you ignore the parasitic heat loss, okay, so the delta T device is basically the number of EC stack n times the delta T ECE. So if your delta T ECE, the property of the material is 3 Kelvin, and you have 4 layers stacked. So ideally, you would have 12 degree, 12 K temperature lift from the device. So if you maximize the heat flux, you still see a significant increase of the device temperature span. So this is what we got. In this chart here to the left, the solid symbols are experimental results, okay? So at the 6 megavolt per meter of EC operating field, a single EC stack, the temperature change is, in this case here, is about 2.8 Kelvin, and a 2-layer cascade, the temperature increase almost doubled, and to 4-layer stack, it's further increase. So the open symbols here are simulated results. So this simulation here motivate us to further, and also shows how we can further increase the temperature lift of this cascade devices. And the cascading actually also increases the heat flux through the polymer layers. All right, to summarize, so the dielectric elastomers feature larger actuation strength and fast response. Okay, so many engineers are developing applications based on this kind of materials for soft robotics, pumps, and haptic devices. The BSEP introduces the bi-stability operation. Okay, so, and it has large variable stiffness. There's also a number of different outcomes from the BSEPs for reversible adhesion and reversible transmittance modulation. So the relaxed ferroelectric polymers is shows larger temperature change. So, and we've been working on designing solid state cooling devices based on materials. So the last comment here is that when you deal with soft materials, so soft materials are organic, which means that through organic synthesis, material formulation, we can generate a large variety of different material properties or functions. On the other hand, these are organic, which also means that in general, they have limited lifetime. On the laboratory scale, so you may also have sort of the consistency or reliable issue from material to material, from device to device. Okay, so I should acknowledge my former and current students and postdocs who have done most of the work I showing here. I would also thank my collaborators and co-workers at the different organizations. So from UCLA, ST Ju, Dr. Qibing Pei, Qibing Yu, he was my former student, is now a professor at Florida State University. And from SRI, Ron Perrin, Roy Combulu on the dielectric elastomers, Tom Libby and Ron on this cooling device, on this, so the PhDE polymers. So we have had excellent visiting PhD students from China over the years. And so I show a few names here who contribute to the work I present to you here today. Okay, so those collaborations with their advisors in China, Professor Tianxi Liu, Cao Zhang from Donghua University, and Professor Zhang Chen Lu Li from Chongqing University of Arts and Sciences, and also Hong Tai-He from University of Electronic Science and Engineering. So we also had the pleasure to collaborate with a team at Microsoft on the BSEP for haptic devices. With that, I thank you, everyone. So I guess this we're now open for questions.
All right, thank you very much. Yeah, let me share my slide here.
Should I unshare my screen?
Okay. So thank you very much, Professor Pei. Let me introduce the panel now. The first panelist we have is Professor Zheng. Professor Zheng is a rising star in soft matter. She's an tenure-track assistant professor at Peking University. She got her BS in 2012 and then a PhD in 2017 with Professor Jian Pei. After that, she went to Stanford, where she worked with Professor Zenan Bao from 2017 to 2021, and then returned back to Peking, where she's now an assistant professor. She's very well published in great journals, amazing work, several papers in Science, Advanced Materials, JACS, Nature Biotechnology, Nature Materials, Nature, among many others. She has many awards. She's part of the 7th Youth Talent Entrustment Project of China Association for Science and Technology. She has affiliation with the Ministry of Science and Technology Innovation under the Young Scientist Project, among many other accolades. So, Professor Zheng, welcome to the panel. Our next panelist is Dr. Tim Giffney, who is currently a lecturer in the Department of Mechanical Engineering at University of Canterbury in Christchurch, New Zealand. He's interested in work on functional materials to build new sensors and actuator devices. He obtained his PhD in 2015 at the Department of Mechanical Engineering, University of Auckland in New Zealand. Then he did a postdoc there and also spent part of his post-PhD time at Peking University. After his PhD, after his postdoc, he took up a job as a lecturer at the University of Canterbury in 2019, where he's been the equivalent of the American assistant professor and is also a rising star in this area. Our first ex-challenger today is Andrew Martin. Andrew got his PhD from Iowa State, and then he moved to Lawrence Berkeley National Lab. His PhD was on metastable materials, looking at fundamentals of the role of surfaces and interfaces on that. And then he switched gears and now is working on thermochemical energy storage systems with salt hybrids. Our second ex-challenger is Dier Fatou Silla, who is originally from Senegal, but is currently a postdoc at Alexander von Humboldt at Dresden University of Technology. She received her PhD in physics from University of Pretoria in South Africa in 2020. And her research is focused on development of novel porous carbon material based composites and their application in energy storage, such as supercapacitor and lithium sulfur batteries. She has garnered a few awards, including the Alexander von Humboldt Award. She had a University of Pretoria postdoctoral fellowship and then NRF South Africa, from the NRF of South Africa, National Research Foundation of South Africa. She has also had visiting PhD research fellowship from Drexel here in the US, among many others. So welcome everybody. Let's jump into the panel. And for the panelists, we will start with our ex-challenges. So, Sela, you want to go first? You can ask some questions, make comments.
Okay, thank you very much, Prof. Pai, for this interesting talk. I have a general question first. Can you tell about your scientific career and the challenges you are facing? From China, you did your BS and PhD. after you did the postdoc in Sweden and after you are here actually in USA. Can you tell us a bit about your scientific career? And the other question is the solid-state cooling device based on EC polymer have advantage on like COP and flexibility, and also the avoidance of greenhouses. So what about for electrical chemical energy storage, such as supercapacitor and also for batteries? Thank you.
Great question. Well, thank you so much. So, a scientific career. So, I mean, so I met challenges at the various stages, from PhD research to postdoc and so on. But now, sort of reflecting back, I've said maybe overall it's too smooth. Okay, so so after the postdoc in Sweden, so I moved to a company in Santa Barbara in California. So the company's main business at the time was started by a couple of professors from UC Santa Barbara. So the main business in the company was about polymer non-emitting diodes. So I was fortunate to be sort of at the very early years of OLED research. So we published some good papers from that company. I guess also because the founders of the company are professors, they like to publish as well. Okay, so that made the transition from industry to academic smoother later on. So from there, I spent a year in Minnesota. A company called eMachine was spun out of 3M. So from there, I learned a lot of, just 1 year, but I did learn a lot of photopolymer chemistry materials. So sort of some of the basic industrial materials, so which actually benefit my research later on quite a lot. So from there, I moved to SRI. SRI International is in the Silicon Valley. SRI is a research company. So I joined the team working on dielectric elastomers. So that's where the dielectric elastomers was initially discovered and developed. So in the same time, I also had a project on OLEDs. And OLEDs was still fairly sort of new, rising at the time. So I worked on those two subjects before I moved to UCLA in 2004. Okay, so at UCL, so obviously based on my experience from before, so we started we call it soft material research lab. So initially the soft means polymer electronic materials. To everybody, most of my colleagues working on electronic materials, polymer is soft. So ours is a soft electronic material. So we work on OLEDs, actuators. So, and from those, we sort of combining this OLED materials, and the dielectric elastomer has the combined electrode, right? So combine these two together. So we introduce a few stretchable electronic devices, such as stretchable polymer OLED and stretchable transistors based on single wall carbon nanotubes. So dielectric elastomers, so that research in my group has always been focusing on materials development. So we try to sort of solve the issues with the dielectric elastomers such that this material could become commercially viable. So we are very happy with the recent development of the PHDE, or the processable high performance dielectric elastomers, because it combines the processability, which is very important, and the high actuation performance. So that's the topic that hopefully we can expand further. I mean, often at a university environment, and how well we can expand the project or the funding. So it depends on how much we can do. in this subject area. So on this electrochloric cooling, very interesting. So we started when, so actually, after we invited Professor Qibing Pei from Penn State University. So he basically invented this PVDF polymer. So I invited over to give a talk to our students. And so thereafter, so we're always thinking about how can we utilize this kind of polymers, the larger delta T. And so we came up with this idea of combining, the electrostatic actuation with the electrochloric cooling. So we were able to show this cooling devices, solid state cooling. So right now this cooling device is still at the very early stage of research. It's not even development yet. So the first barrier we need to overcome is that the temperature lift from the device must be high enough. So high enough means that we're talking about 20 degrees Celsius temperature lift, and we are not there yet. So hopefully we can. I think in principle it's doable, but there, practical challenge, there are plenty of practical challenges out there to increase the delta T. So once the delta T is there, we can seriously develop cooling devices based on this kind of materials. I think that right now it's again it's too early to say, but I'm confident that eventually these solid state cooling devices can compete with the vapor compression cooling in performance, and then it has this added benefit of being compact, solid state. So there is no HFC coolant used in these solid state devices. So that definitely will be a significant improvement in reducing the greenhouse gas release.
Yeah.
So the polymer you asked that has high dielectric constant, very high. So it's also useful as a energy storage material. So people are reporting energy density of over 10 joules per cubic centimeter from this kind of materials. And so that would be a very high value for a capacitive energy storage. Okay, so that's something we are interested too. Yeah, there are a lot of possibilities with this PVDF polymer and that category of polymers. So long answer. Well, thank you.
Thank you.
Very good. Andrew?
My question would be more towards the electric elastomers. I see your work and I see you basically growing this idea of like using PHB and just build upon that, trying to add things into it, trying to fix one problem at a time and things like that. But is there, because in principle, it's just a dielectric polymer that can have a strain response to an electrical field. So why is it that you decided to just build upon this one material instead of like branching on like a lot of different material and trying like which ones would be the best candidate? And the other question is regarding to that as well, is that as you were starting to wanted to become a professor and things like that, how do you grow your idea in a sense that that the idea that you're bringing into a university is a scalable one, and you can like have a lot of, because I see like you have a lot of students in it, and there's only when you started with something, you just have like one idea, you have one big idea, right? And then you have to branch it out into like having to support 10, 20 students, like having them have something to do. So yeah, that's the question.
Great. So the first question you had, so can you clarify? So are you asking the formula for the PhDE So why we settled with that specific formula, or what's the flexibility of expanding the formula to other materials?
Yeah, it's kind of a little bit of both like that, because from what I saw, it's just you started with VHP, right? And you started to add more stuff into like making a composite out of VHP, basically, right? You added a carbon nanotubes into it. You added more different polymers into it to fix like one of the stress problems one at a time.
All right. Okay. So, the PhDE. So the PhDE is, it's a sort of developed over many years. So we started with an early version that also the bimodal network structure. So, but the performance of that system was limited in the maximum actuation strength, and the energy density, and also response speed. So then we were lucky to have a project funded by DARPA, which, that means that we can have multiple students looking into the formulations. And so we look at, say, literally hundreds of different formulations. I mean, so in a way, the underlying or the guideline in this formulation was that we know what kind of, roughly at least, we know what kind of stress strain relationship we need, and we also know what what material, you add a new component into the formula, and you modify the property of that system. So we tried many different combinations. So we settled down eventually with the PhD. I mean, I'm pretty sure the PhD formula can be further improved. It's just that, so now we have to pick a formulation to expand into sort of devices and so on. So the carbon nanotube is in the PhD case is not mixed. It's not mixed into PhD. It's coated onto the PhD film as the compliant electrode, so that we can apply the voltage to the film. So there are research out there, because the dielectric response is proportional to the dielectric constant. So there are efforts out there, not by my group, mostly by other groups, to increase the dielectric constant. So one approach is when you add a small amount of fillers like carbon nanotubes into the system, you could potentially increase the dielectric constant of the material. There are a lot of challenges in that direction as well. What's your second question?
How, I mean, like you started, I assume that you probably like started with like some ideas coming into like university, trying to become professor, because you work in industry as well, right? And you brought some of those ideas with you. How then do you kind of expand that idea into something, a project that can, support 20 plus students at a time, having students have something to do, each every one of them being unique, right? Because everyone has to write a thesis at some point. How do you have the brain to kind of branch those things out, like every like still a little bit at a time?
Oh, good question. Well, the thing is that when you have 20 students, you have 20 brains. Okay, so
yeah.
Yeah, I mean, so it's like it's in the university research group. So the ideas are driven both ways. I mean, some are by the faculty advisor, some are by the students. I mean, usually when a new student joins the group, right, they work with the existing students on specific topic areas. Then the new student and everyone could come up with new ideas based on what they learn about the project or what can be done in the group. So in a way, the expertise, the facility in the group somehow sort of impact what new ideas could come out of the group. So I mean, sometimes that we'll say that the professors are project managers, so in a way, we don't spend a lot of time in the lab doing research. We talk to people to get, a lot of time we talk to other people, so, you get ideas from what others are doing. And also we try to get funding to support our students. So yeah, new idea comes from many different sort of sources, from through collaborations from students. New students come in, you bring new blood.
I think Andrew is asking for the magic sauce for being a professor, and the reality is you have to keep going on. You start with an idea, you look at the data, and you let the data tell you what it is. You have to be aware and present, and it's a very, very good question, and a daunting one, definitely for somebody who's starting out. Very good. Why don't we jump to our other panelists? Tim or Professor Zeng, you can jump in.
Okay, so first of all, is it my turn?
Tim, you're breaking out, so let's go to Eugene. Yep, go ahead.
Okay, thank you. Thank you, Professor Pei. It's great talk. And I think I've only listened to your talk about your other parts of the research group. It's about OLED, especially stretchable OLED. But this time it's the first time that I listened to your talk about the dielectric polymers. It's really interesting and wonderful work. I have two questions about the dielectric elastomers. The first one is that I realized that for PhD, the recent work that you published, it's the performance of the elastomer is really great, but the electrical field that you apply to the elastomer is still extremely high. And so the question would be, one, is this a problem that we need to solve or not? Two, if it is the question that we need to solve eventually, then is there any possibility that we could reduce the electrical field, but still maintain the same same deformation? And the second question is about the deformation, the aerial deformation that you mentioned in PhD that it can reach 190% aerial deformation, and what kind of level it is, like for example, for our human muscle, how much deformation that we could achieve, and for which kind of application that we need such a high level of aerial deformation. Thank you.
Thank you. Good questions. So on the PhD, so the operating field for the maximum strain is high. Yes, I agree. It's very high, and so the maximum stress. Okay, so it's proportional to the square of the electric field. So usually, when we design new materials, we look for the breakdown field strength. So that determines the ultimate performance of your material. And so the high voltage, high field itself, it's not necessarily a problem. It's the driving voltage. Okay, so right now we drive our PhD films at about 2 to 4 kilovolts, and that's a high voltage. Okay, so people always argue that these voltages are too high, unsafe. Okay, so but on the other hand, these are capacitor devices, so the current flow through the device is very low. So I mean, ideally, you want to. I mean, from our experience so far, the main challenge dealing with high voltage is switching. Because right now, high voltage switching, the switching device you can buy are for high power applications. So high voltage, low power switching devices are not readily available. Okay, and but it's not fundamentally impossible. It's just that there's no market out there. So I mean, definitely that if we can reduce the voltage, that's certainly helpful. And this could be done in two different approaches. One is simply just reduce the thickness of the polymer film. Okay, so and our typical film thickness is around 30-40 microns. Think about if you reduce the thickness to 3 to 4 microns, then your voltage drop to 200-400 volts. I mean, so the physics doesn't change, and it doesn't change much, but the challenge is to fabricate the film, thinner films at a high sort of yield. That's not easy. At least at a laboratory scale, it's not simple. There are many groups. We also did some of that to increase the dielectric constant. So a typical PhD dielectric constant is on the order of 4 or 5. And think about if you can increase dielectric constant to say 40, 50, then you can reduce the driving voltage by the square root of 10, by 3 times or 5 times. Yeah, that's an interesting research field, and again, there are still a lot of challenges to bringing a new dielectric elastomer with high dielectric constant while maintaining all the other good stuff like high field strength and high actuation strength. It's a work ongoing by many groups. The second question you asked was what?
The aerial deformation that you mentioned.
Oh, okay.
190%. Yeah.
Yes. It's human muscles. So natural muscles usually the strain is around 10-20% maximum for natural muscles, and so for these artificial muscles, and so definitely 10-20% strain would be good enough for a lot of applications. But we are not limited by the natural muscle, what natural muscle can do, right? So we want to build Superman, not just a humanoid robot.
Yep. Very, very interesting. Tim, do you have a question?
Let's try again. Professor.
You can. Tim, your audio is not very good. Hello?
So Tim, you probably have 2 mic at the same time.
Am I coming through right?
No.
No.
Do you mind typing your question on the chat?
My apologies.
Oh, now you're clear.
So first of all, Professor Pei, thank you for your wonderful talk. I felt that in this field that for a long Professor Pei, I'm curious. Well, Professor Pei, thank you very much. That in a field that has concentrated EHB and silicon together with carbon grease electrodes, your work to engineer the polymers themselves has really pushed this forward. And the question I hope you could help answer with your broad experience of this field, how do you see the wider field of soft actuators developing in the future? I mean, we've got the conducting polymer actuators, the IPMC actuators, various new types of soft actuation technology. I know you mentioned Christoph Kepler for DEAs. I know he also works on zipping type Hazel actuators. I just wondered where you see sort of sparks of promising light in the field of soft actuators in the years ahead.
So Tim, I couldn't hear the full
So I think
question.
Tim is asking about where you see the future field of soft actuators going in the next 5 or so years. Maybe you can comment on based on where the research is, what the future looks like, and
So
where
I
you think the
got
field is
part of-
moving.
All right, so I got part of your questions about comparing, say, dielectric elastomers with other electroactive materials like conducting polymer actuators
Mhm.
and the Hazel devices. I suppose that's your question. So different materials have its different characteristics. So I would say that depending on what exact the application you want to develop, okay, so you would choose the material that works the best. And for dielectric elastomers, so the attractive part is the high actuation strength and energy density and fast response. But on the other hand, the high voltage is an issue for many people. I mean, so a lot of companies, when we talk to, right, so they would not accept putting 1 or 2 kilovolts on the skin, for example, right? So in that sense, the conducting polymer operating at only 1 or a few volts, that would be very attractive. And there's also these IPMC systems that also operate because it's an ionic system, so the operating voltage is low. And the Hazel device share a lot of the same challenges we have in a way. They are also high voltage. And the Hazel combines fluid, dielectric fluid in the system. So the attractive part is that the fluid can distribute the force, So and also the fluid has this kind of problem. The problem they call self-healing. So in a way, when you have a dielectric shorting event, the fluid can sort of blur. I call it blur the effect, So that's very attractive. So I mean, again, that the Hazel devices share a lot of similarities and the challenges with the dielectric elastomers. So going forward, so right now it seems like there are more sort of people, particularly from the mechanical engineering or electrical engineering fields, looking into utilizing these kind of materials to design functional devices. So where do I see where would be the sort of the first few products coming out of these? I mean, there are already companies making devices or products using the sensing function. So, these soft materials, right? So you apply voltage, you generate deformation. On the other hand, from deformation, you generate voltage or current output. So you use that as the sensor. And the sensing function does not involve high voltage. So that may be the reason why the sensor became the first sort of generation of products out of these. And so actuation, I mean, eventually that's the sort of what's sort of fundamentally new to the table from these electroactive materials. It's difficult to predict where you see the first product. I would say it a lot depends on which company pick up the technology to develop. So I worked on OLEDs before. So at the time we were working on OLEDs, so the main concern was about lifetime. You're driving organic material at high current density. How can you have high stability? But then, large companies like Samsung, LG, they pick up the technology. I'm sure they invested, hundreds of billions of dollars. They make the OLEDs now stable enough for TV sets or computer display screens. So I'm sure that if larger corporations that commit to the technology, and we'll see the products. So at this point, it's up to say which companies start to look into these technologies.
Thank you, Professor Pei.
Yep, thank you. Yeah, thank you very everyone, and Tom, Tim, thank you very much. I know you're having challenges with the internet out there, but we thank you for your participation. So for now, I'm going to switch gears and bring us towards the conclusion. And I want to thank Professor Pei for your time and wonderful talk, and for the panelists and our ex-challenges. So Professor Pei, we will send this virtually. Please accept this certificate. If there was no more times, we would walk across the stage and hand you over this certificate. But now, please accept our acknowledgement for being our speaker for the 125 volume of ICANX. Thank you very much.
Well, thank you, Martin. Yeah.
Yep.
Well, thank you, Martin, for having me, and thank you all the panelists for the great questions.
Thank you. And then I want also to remind everyone about our upcoming Young Scientist Award, which is going to be on December 2nd. Please join us as we listen to this young rising star give this a highlight of their work. We have 24 of them. So we will be listening to them in several days. These are the speakers on the 2nd. Then we'll switch to the second cohort on the 9th. And the last cohort is going to be on the 16th. Fascinating, great global participation in this Young Scientist Award ceremony. And with that, thank you, everyone. Please join us next time. And I won't sign off without acknowledging our sponsors as displayed in the screen here. Thank you, and have a wonderful Friday.